Whiteface Mountain is the fifth highest mountain in New York State and sits relatively separated from the majority of the rest of the Adirondack high peaks. Routine temperature measurements have been collected at the summit since 1937, and since 1957, a large suite of other atmospheric and meteorological components have been incorporated. In 1976, the University at Albany Atmospheric Sciences Research Center began regularly collecting cloud water to check for trends in the cloud water chemistry. Whiteface Mountain is an ideal location for this kind of data because its removal from large, populated industrial areas makes it a good background or baseline for what's in and moving through the atmosphere, rather than what's being emitted into the atmosphere from a source nearby. The summit itself is about 1.5 kilometers or 1 mile above sea level, and sits about 50% of its time in cloud, as seen from this camera near Lake Placid, New York. When that happens, it provides an eerie, otherworldly view and allows us to directly intercept the clouds with our sampling equipment. But how do you collect a cloud? And why would you need to? First, what are clouds? Clouds are tiny droplets of water suspended in the atmosphere after a parcel of air has passed the point of critical supersaturation. That just means there's more water vapor in the air than can be held at its current temperature and pressure, so the water vapor is forced to condense into droplets or ice crystals around cloud-condensing nuclei or ice-nucleating particles. So, you've got a remote mountaintop research station, you've got a cloud. How do you catch it? The ASRC uses a deceptively simple and ingenious mechanism developed by Dr. Volker Monin. The Monin Omnidirectional Cloud Water Collector works through inertial impaction. When the collector is deployed, the clouds are usually moving at least 2 meters per second, or roughly 4.5 miles per hour, across the summit. This diagram from Lawrence et al. Gives a more detailed view, but basically, the cloud droplets have inertia and they impact the Teflon strings of the cloud water collector. They grow until they're large enough for gravity to pull them down, and they arrive in a special collection system where we currently combine them into 12-hour bulk measurements of whatever clouds might have been passing the summit at that time.
We are equipped to measure how much arrives. We are equipped to find out from what direction they came from, but at this moment we are not yet equipped to find out where they have originated.
We can actually get an idea of where the air parcels impacting the summit have come from using NOAA's hybrid single-particle Lagrangian integrated trajectory, or HISPLIT model. These are where cloud water samples, on average, were coming from between 2014 and 2021. But why? Well, each cloud droplet can act like its own little test tube. Atmospheric gases and particles can get incorporated into the cloud droplets, and chemical reactions can take place. And the results can be not great.
The rain! It burns! Skin is on fire! Why is the rain doing that?
Acid rain and smog, for example, were very prevalent in the latter half of the 1900s. They're the product of photochemical and aqueous chemical reactions from the exhaust of certain combustion engines and factories. In the case of acid rain, things like sulfur dioxide and nitrogen oxides dissolve in cloud water and turn into sulfuric acid and nitric acid. These then deposit themselves across the region in precipitation or fallout. This was hugely problematic for ecosystem health, among other things. For example, look at this 1991 New York Times article telling people the best thing they could do for their car after it rained was to wash off the acid deposition before their paint eroded.
First order of business is to clean up this acid rain with a little...
The 1990 Clean Air Act amendments aimed to tackle problems that persisted after the original iterations of the Act, with Title II addressing vehicle exhaust and Title IVA addressing acid deposition.
Sitting up here on top of Whiteface Mountain and watching the world, one certainly would like to see the air cleaned up.
Continuous collection and chemical analysis of cloud water and precipitation shows the extraordinary success of this policy, with drastic reduction in sulfate, nitrate, and ammonium ions, and a steady increase in cloud water pH. We can also see significant improvement in the acidity by looking at the ion concentrations of sulfate and nitrate from the National Atmospheric Deposition Program between the 1980s and the mid-2010s. This is a great example of how science can drive policy, and how, if we have the will, we can make progress towards a better future. I've included some more information about the Whiteface Mountain Field Station, some information about cloud water chemistry published by my colleagues recently, and some information about the acid deposition program and source material in the description. Anyway, thanks so much for watching. We're quickly on our way to 11 bajillion subscribers or whatever, so, you know, push some buttons. Something.